Hey, welcome back to your favorite pre-calculus class. We're going to talk about exponential growth and decay models as well as Newton's law of cooling in this section. So let's start with, there's a lot of natural phenomena that follow the law that an amount V varies. So the amount that you have varies according to the time t, where a subscript 0 is the initial amount, because if you have time t being 0, you'd have e to the 0, which is 1, so you just end up with a subscript 0 being the original amount. For example, you may have exponential growth situations, like colony of bacteria, like we'll talk about, or you might have some decay situations where you're k constant. So this k constant part, that's like your growth rate, okay? If it's positive, you're going to have a positive, exponential growth. If you're negative, you're going to have some sort of exponential decay on that. So let's look at uninhibited growth with cells for a minute. Instead of A of t, they just call it n of t. Instead of a subscript 0, they call it a n subscript 0, but n of t is the amount that you end up with after time t. N subscript 0 is still the initial amount in the cells. So let's do this example here. If n is the number of cells, t is the time in hours, express n as a function of t. So this is just saying, just write the function n subscript 0 e to the kt. Okay, that's part A. Let's do part B here. If the number of bacteria doubles in 3 hours, so whatever you started with n subscript 0, you're ending up with doubling it. So you have double what you started with. So n subscript t becomes 2 n subscript 0. Again, n subscript 0 is what you started with. And it happened after 3 hours. So t, your time, in hours here, put a 3 right there. And then we're just going to solve for k so that we can find this function. We can find what our k, what our growth rate here is for this. Let's divide by n subscript 0. That's gone. So we got 2 equals e to the 3k. Take the natural log on both sides. And so you've got ln of 2 equals ln of e to the 3k. Just bring down that 3k. Divide by 3. So k equals 1/3 the natural log of 2, which is, if you punch that in, 0.23, approximately 23105. And I would take that out a good 5-6 decimal places so that when you're working with this k, because now we're going to write the function with k in it, n of t, the number of cells we have after time t is equal to the initial amount, e to the k, 0.23105 t. Okay, so here's our function. It gives us the number of cells in the culture. How long will, let's see, how long will it take for the size of the colony to triple? So how long, t hours, we're going to solve for t hours. How long will it take to triple? So part C, you're going to say, well, I want to triple the amount I started with, e to the 0.23105 t. Now we're just solving for t. So we get rid of n subscript 0, get rid of n subscript 0. 3 equals e to the 0.23105 t. So we're going to find how many hours here. Undo e with the natural log. ln of 3 equals 0.23105 t. Divide by 0.23105. Divide by that 0.23105 t. Punch this in, and you get, let's see here, about 4.755 hours. 4.755 hours. So 4 hours, and then 0.755 times 60 minutes, of course, would be about 45 minutes. 4 hours, 45 minutes. Okay, so that's part C. Part D, how long will it take for the population to double a second time? So, well, if it doubled in 3 hours, I mean, you could use the equation again, but if it doubles in 3 hours, then it's going to take 3 more hours to double a second time. So a total of 6 total hours. And these are just looks at those as well that we worked through. All right, but what about the law of decay, uninhibited radioactive decay wouldn't be an example of this. So your K is going to be negative. Okay. A subscript 0, so your initial amount. So here's an example. You got traces of burned wood with ancient stone. Tools in an archaeological dig in Chile were found to contain approximately 1.67% of the original amount of carbon-14. If, and here's where you want to start, if the half-life of carbon-14 is 5,730 years, approximately when was the tree cut and burned? Okay, so that half-life right there, that half-life, 5730 years, that's going to tell us how the growth rate on this thing. In other words, how fast it decays. Okay. So we're going to use this equation, A of t equals A subscript 0 e to the kt, and we're going to use this to find our k value, which should be negative here. So if the half-life of carbon is 5,730 years, that means you end up with half the original amount that you started with of this carbon after 5,730 years. Okay, divide by A subscript 0, divide by A subscript 0. Take the natural log on both sides, so the ln of 1/2 equals the ln of e to the 5,730k. So then I've got 5,730k equals the ln of 1/2, or the ln of 1 minus the ln of 2, however you want to write this. Use and k. This ends up being, again, I would take this out really far so you don't have rounding error when you're going to use this. Okay, there's your k that you're going to use. So now, step 2, now we know k, so we can write the equation with k, and it says traces of burned wood were found in a dig that contained approximately 1.67% of the original amount of carbon-14. So we end up with 0.0167, 1.67% of the original carbon-14, okay, is what we end up with. So that's our A subscript, that's our A of T, right? We get 1.67% of the original amount. Equals the original amount, A subscript 0, e to the k. Now we got the k, negative 0.00012096.8 times t. And we're going to find our t so we know when this tree was cut and burned. Okay, divide both sides by A subscript 0. Both sides here. Take the natural log on both sides. And then we're going to divide by that negative 0.00012096.8. And once you do that, your t will end up being 33,830 years. That's how old. That's when that tree was cut and burned. Okay. Alright, let's talk about Newton's law of cooling now. So the temperature of a heated object after time t. So that's U of t. How much the temperature after time t. So temp after time. Okay, is equal to t. So this capital T right here is the temperature of the surrounding medium. Okay. And that U subscript 0, this is the initial temperature of your object. K is still a constant, it'll be a negative constant. T is still time. So K is the constant there. So that's how fast it cools off. Like maybe you have some sort of, I don't know, one object might cool off faster than another, right? So you're going to have a different K constant there. So let's do an example of this. I think this will make some sense here. An object is heated to 100 degrees Celsius and then is allowed to cool in a room whose air temperature is 30 degrees. So let's imagine like I don't know, you cook your brownies in the oven and they're heated up to 100 degrees Celsius, right? And then we pull those brownies out and put them on our cupboard, and that room temperature is 30 degrees Celsius. Okay, if the temperature of the object is 80 degrees after 5 minutes, when will its temperature be 50 degrees? So we're going to use this formula, U of T equals T plus U subscript 0. Let's see, it was minus T e to the k T. Alright, so first of all, an object is heated to 100 degrees Celsius. So right when we take them out of the oven, it's 100 degrees. So that's our U subscript 0, 100 degrees Celsius. Okay. It's then allowed to cool in a room whose air temperature is 30 degrees. So this is the temperature of the surrounding medium. So we put it in a room. Eventually those brownies are going to be 30 degrees. So that's the capital T. That's our 30 degrees surrounding medium. Capital T. Okay. So we have U subscript 0 is given, capital T, the surrounding temperature is given. Now let's go to part A. If the temperature of the object is 80 degrees after 5 minutes, so it ends up being 80 degrees after 5 minutes. 5 minutes is your time there. Okay. What's our K constant? And then we'll finally solve when will its temperature be 50 degrees. Okay, so we got 80 equals 30 plus 70 e to the 5k, so let's subtract 30 both sides, subtract, gosh dang, 30, so we got 50 equals 70 e to the 5k, divide by 70 both sides, so we got 5/7 equals e to the 5k, take the natural log, so we've got, I'm going to write ln of e to the 5k is 5k, I'm going to put the 5k over here, equals ln of 5/7, divide by 5, so 1/5 the ln of 5/7, okay, so that's approximately, you punch that in, negative 0.0673, I'll go to, should be okay there. I'll follow the slides on that. So there's our K. Now, when will its temperature be 50 degrees? So this is still all part of part A. When will its temperature be 50 degrees? We know this. So when will it be 50 degrees? So we have this formula. The room temperature is 30. We're starting out at 100. We know our K, negative 0.0673. When will its temperature be 50 degrees? Well, we're going to solve for T here. When will this be 50? So I'm going to replace that with 50. We want it to end up being 50 degrees. Okay, subtract 30 both sides, so now you got 20 equals 70 e to the negative 0.0673 t divided by 70, divided by 70. Now you get 2/7 equals e to the negative 0.0673 t. Run the natural log. And now you've got this over here. So we're going to divide by 0.0673, divide by 0.0673. And your time is going to be 18.6 minutes. 0.6 minutes, 18.6 minutes there. Okay. So part B is a similar question. Determine the elapsed time before the temperature of the object is 35 degrees. So now you can go on and you say, well, this time I want it to be 35 degrees. I still have the surrounding medium 30 degrees. Here's our 100 minus 30 right there. I know my K, and we go through and we solve for T, and it ends up being 39.2 minutes. So back to this here, last question. What do you notice about the temperature as time passes? What do you notice about the temperature? So these brownies, I pull them out. They're initially 100 degrees. I pull them out. The room temperature is 30 degrees. Throw them down on the cupboard. Of course, again, the temperature is 30 degrees in the room. Well, as the time t goes to infinity, in other words, the limit as t goes to infinity, it's called in calculus, eventually, what are those brownies' temperatures going to be? Well, eventually, it's going to be 30 degrees Celsius, right? It's going to be room temperature if you leave them there long enough. Okay, but you can find now how long it takes to get any temperature, or after 10 minutes what the temperature will be. You can find all this with Newton's law of cooling. Well, thanks for listening. We'll see you guys in class.